So I want to talk about an idea I have to kind of make a Martian or a lunar brick or brick on other planets that can be a good insulator or conductive depending on how you make it. And will be cheap and easy to manufacture relatively. So first idea is you put in the Martian soil into a little box like this. Into the part of the box you pump in either carbon monoxide or hydrogen, depending on the local resources. This then is brought pretty hot, and what it does is it does a couple of different things. It first can melt some of the particles that have a lower melting point. It'll be able to melt some calcium compounds, some of the salt compounds, but a lot of them it won't be able to melt. The other thing it can do is it can reduce some of the stuff. Reducing is turning something from an oxide into a non-oxide, like a metal. When something is reduced at a high enough temperature and enough pressure, they fuse together. And that can be a lot lower temperature than its actual melting point by 1,000 degrees, and very common thing to happen. An example of this is that if you heat up a brass on a brass versus metal on a plate, and you just heat up a little bit, you can actually coat stuff with brass. Under pressure, it's even more. And under the conditions that we're doing it, these dust and soil will do it even more, as they will be changing its form, because it'll go from a crystal with one structure to a metal with another structure, and it changes it. And when it's rearranging it, it's more easy to stick to other things, as its size is expanding and cooling also causing pressure. Then on top of it, you have a pressure plate that presses this whole thing down to also press and compact it. As it's changing molecular structure, it just fuses the whole thing together. And this is a lot less energy also than melting the whole thing, because you only have to heat up the outside of each of these tiny particles that make this. They can be as big as gravel, tiny, to do it. So all you have to do is fill up the mold. Now on the outside, you might want to press it and fuse it more to kind of make it a solid thing that's not porous. But that might not be necessary for inner layers or stuff like that. Or you could simply paint it in areas. And then you could adjust the thermal conductivity of these things, so make it insulator or non-insulator, but either reducing it more, which makes it more metallic and a better heat conductor. By compacting it more, makes it also more conductive. Or you can have big blocks that are not conductive or very porous. There's a lot of other things you could play around. You could play around with the composition a lot by using different soil samples and all these different things. So then, that is the first part. But then there's CO2 and water, which is what the chemicals are given off, and maybe a little halogens. Halogens are toxic, but they're not going to be pumped out everywhere. Goes into the step reactor. And what the step reactor will do is it will split off into oxygen and halogens, which go in one direction, and carbon monoxide and H2, which can be used, repeat a cycle. And that recovers a lot of the heat. A lot of the heat that is, whenever these stuff react with all this process that happens in here actually creates heat. So you have now some of the heat is lost in heating up the material, but it's also heat created. So it kind of, we don't know if it balance out exactly, but the gas coming off also hasn't transferred all of its heat. So you have a lot of heat back up here. Now this stuff is repeated, and now here the oxygen can be used for fuel or for human beings just breathing. And the halogens, and by the way, this process that I'm going to propose is more efficient than plants making oxygen. The halogens can be used for a wide range of things. They can be used for making plastics, to UV protection and stuff like that, to disinfectants, but they are slightly toxic in many forms. and there might be many nitrogens, or you can just pump it outside. You might be able to recover some of the heat from it using fancy heat exchangers like heat pumps, which could be a very efficient way of recovering heat, actually, heating up the whole thing. You could also use it for rocket fuel, but that'll make very toxic rocket fuel, but powerful, potentially. Now, how do we split it up? Well, I'll put some link there, but this research group that I've helped work with has invented the step process. And what the step process does is it can really, really efficiently split a bunch of molecules, including calcium carbonate and make lime. It can make carbon nanotubes out of CO2. It can make iron out of iron oxide. It can make aluminum out of aluminum oxide. Well, that's been theory, but it's proven with iron, carbon, out of a variety of ones, from salt to carbonates to oxides, with all those different forms you can find in nature. You can also make silicon out of it, little trials of magnesium. But it can split up all the stuff, and it uses the heat from the sun to lower the reaction potential. Roughly, you need, if you heat it up according to Kelvin, there's a linear decrease with the amount of heat you need the higher temperature to get. So if you heat up to 800 degrees Celsius compared to room temperature, you need about, you have a linear decrease. There's a linear parameter. How fast linear goes down is different for different chemicals, but quite significant. It's actually more efficient than a heat engine, like a car engine stuff to drive this stuff. It can beat the theoretical full efficient heat engine. It's one of the most efficient ways of using energy because it doesn't rely on the Carnot cycle, which Carnot cycle relies on the heat difference. This actually relies on the actual energy in the heat. The other thing, then you melt these compounds. This is an example with iron, but you can also use ammonia, a bunch of other things. You melt these compounds. Well, that's ammonia. This is the CO2 example, which I'll try and make it big. But what you could do is then after you melt, let's pretend it's just the iron. You can ignore the ammonia part. If you ignore the ammonia part, the iron the iron is then split off this with electrolysis, which is you put electricity on, and one thing you produce one chemical, another one you produce oxygen. In this case, we're producing carbon monoxide, which is produced around 850 degrees Celsius, which is also the same temperature that lime starts to form from limestone, and can make the really strong cement stuff. So it's a perfect temperature for that. If you have a lot of lime, and there's a lot of lime-related chemicals in a lot of these soils from Mars and also from the moon. And the rest of it, then in this bath, the trick is, what makes it so good at electrolysis is that it uses a molten carbonate, which, because it's a liquid, it can move around ions really fast, which means it's very conductive for ions, which is what you want in electrolyte. Compared to solids, where the chemicals can't move around as fast, so it can't go into the electrode and get discharged, or go here and get discharged. It can't carry around charge. And in electrolysis, you want the actual molecules to carry the charge by ions, which means they either have if every molecule atom has a positive or negative charge, not through like metals where it's carried through with the ocean through everything, or like in conductors. And carbonate and liquids have a higher ones because of how molecules is pumping into each other and being more mobile themselves. Another thing that makes this process so efficient is, if you're looking at the one that we would use for space, we would use lithium carbonate. And lithium carbonate, or the other carbonates, have CO3. It's Li2CO3 is lithium carbonate. So that is 2 lithium atoms, small, 1 carbon atom, and 3 oxygen atoms. And CO3 is in the negative part. Or you can have sodium carbonate, which is 2 sodiums and the rest is the same, and so on on mixtures. But that carbon is super high concentration, and the CO2 part of it is even higher concentration, which means that there's a lot of energy goes into splitting the actual molecule and not elsewhere, and it actually goes up pretty rapidly with concentration, how efficient this whole thing is. And it's more dense. And this whole thing means that it's very efficient. We're talking about efficiencies above 70 to 90% for energy goes in, comes out. And you can also use solar cells and stuff to power this whole thing without relying on expensive chemicals because everything is used up. With water, it can be more or less efficient depending on the temperature you're looking at. But it can do both at the same time and more. Also, it can make chlorine and stuff like that. So anyways, these stuff come off here. And we have the hot oxygen. And also we can recover some of the heat from the oxygen here with heat pumps and stuff, which could cool down the oxygen to a nice temperature and heat everything efficiently. You actually put in with heat pumps. If you use heat pumps to cool down these leftover gas, you recover more heat than you put in to make that. So actually you get more than 100% efficient. It's a trick because you actually also get some of the heat from the sun, but the trick works that you're actively pumping away heat from here into here. So it's not only a temperature difference of putting 50 degrees, if it's 60 degrees Celsius, and this is 10 degrees Celsius, just making up numbers, and those numbers are way too low. This will, the energy requires to pump 50, we can pump 51 degrees Celsius, and the energy requires less than, will require to heat up 51 degrees Celsius, because some of it's from pumping. It's kind of cool that way. So this whole thing will be very efficient, and yes, there might be some leakage, but a lot of it's regenerated, so we can reuse CO2 and water over and over again. So leakage might happen, but we don't have to worry about getting CO2 and water in site as much. Now, can we get CO2 or water on site to split it up, or hydrogen or carbon? We actually just need hydrogen and carbon monoxide. Even just carbon. Well, Mars' atmosphere is 95% CO2, and we need very little. There's also evidence of water very much in different places, and methane in organic compounds, and there is some carbonates. The moon is a lot harder. There is some water, there is some carbon, but it's very low concentration in most places, so we probably have to bring it along with ourselves and seal the whole container more. So I want to show you the composition, and we can see the composition has it's pretty much oxides, but it's actually not as oxidized as a lot of earth stuff with chemicals. It has a lot less carbon in earth stuff, but that's from Mars soil. A lot more metallic, and calcium oxide, which makes a lot of it. That stuff would melt at these temperatures and would fuse together well, and that's what we use to make cement. Sulfates are also common in cements, would work, and phosphates too. Silicon oxide, magnesium oxide is also very similar to calcium oxide in those properties. So majority of it would be pretty fused easily and fuse the rest of the stuff together, at least for lunar stuff. There's also an effect going on that's a eutectic mixture, and a eutectic mixture would lower the melting point of everything even more and make stuff fuse more easily. And that's if you have all these complex chemicals together. The melting point, and the other points where they change, like the crystal structure is a lot lower than normally would be. And the reason for this is, imagine like a water molecule. Maybe I can find a picture. Couldn't find a picture before. Salt. But so water molecules, normally if you look at water, see these ions, which is something they found in salts. In this case, it's sodium chloride table salt. Kind of mess up the water overall structure, because normally water wants to form a nice hexagon pattern, where I'm going to show water ice. Molecule. So that's like the perfect stable structure and stuff like that. But anything that's sodium or chlorine in this thing, they disrupt that structure. They can't fit in it as well, and anything else, almost. And you can look at salt molecule. Even though there's a bunch of different salts, so I know it's not accurate, but they form a nice cube that water doesn't, so you can't have the salt in it form nicely. Another thing, besides this disrupting the basic structure so that everything can't fit together, the lowest one, is that these ions attract stuff, so they also disrupt it from an electronic thing, where all the negatives are facing, and you have an outside positive, which then causes a big, large-scale disruption, because it causes that to kind of neutralize stuff that would normally stick together. Kind of like if you have sticky duct tape, and you take another sticky duct tape and put the two sticky things together, there's no more sticky, it's both not sticky on both sides. And it kind of disrupts that, so it disrupts the bonding that way, and not only can you not find that structure as much, there's more pieces to fit together, so it's hard to fit everything together because not all the pieces are identical, so it's there's more ways it can get messed up, hard to fit everything together. Also, everything, because of different weights and sizes, are moving around at different speeds in different ways. Water has more rotational energy, but it's slower in other ways. And then it can also disrupt other things, like more complicated, like water is not actually pure water in what form. There's hydronium. It can have an extra hydrogen here for a little bit, or it can have one less hydrogen, and that happens on and off all the time. Stuff like that, so all this stuff disrupts it. Now, we're not talking about water, but we're talking about other chemicals with a complex mixture. And for metals and oxides, it's usually 2 to 2. So all this stuff will kind of disrupt each other and make it change more easily under temperature, promoting it. Now, this would work for a very wide range of compositions of soil, but we would have to test it out to figure out the exact parameters to make it nice. Not that we can't make it, but if we really want to make it nice. Now let's look at lunar soil. Lunar soil is almost 99% of these elements, so there isn't really a lot of carbon and hydrogen, unless maybe you land on very specific locations. But again, these are similar elements that we can fuse easily. And calcium, by the way, a lot of calcium compounds really lower the melting point of silicon compounds. And that's how we make a lot of glass with calcium flux. Or more commonly is potassium flux, and sodium, which is potash glass. Which there's also kind of significant amounts of that. Phosphorus. So after we melt and fuse it, we can play around with it. Well, thank you very much. Oh yeah, and even if we make it in different ways, there's further cool things we could do. Like we could make it in different ways and actually use it to store electricity, because you can make one of them more or less electronegative, and people have started to make that into capacitors, which is a way of storing electricity. So a very simple battery you can make. That's not very dense battery. It won't be, for density or weight, it won't be very good. But you can make a lot of them cheaply, and they could discharge quickly. You could also use them for making structures that absorb heat very well and just keep the heat in, for like solar energy maybe. Maybe roads for rovers, which would be very efficient with tiles, because roads, stuff moves a lot more fast because it's flat and less friction. All these possibilities. Well, thank you very much for listening. Please like and subscribe. I'm trying to reach 1,000 subscribers in a year and 4,000 watch hours, so I can do this better, so my channel can get promoted and my channel can promote it more and more people can see it. Also, if any idea for future videos, comments, or suggestions, leave it in the comment section below. Thank you very much. Goodbye.